In this video, we take a look at the different kinds of thermodynamic processes that a system may experience or undergo. First, we have the adiabatic process or adiabatic process. An adiabatic process is characterized by no heat transfer into or out of the system. That is to say, Q is equal to 0. You'll recall that our equation from the first law of thermodynamics, delta U, the change in the internal energy of the system, delta U is equal to Q minus W. If we set Q to 0, that leaves delta U to be equal to negative work done, negative W, where W is work done by the system or work done on the system. Any increase in energy typically translates to an increase in temperature and vice versa. In the figure to the right, path 1,4 is an example of an adiabatic process. So from initial state 1, the system transitions to final state 4. The temperature changes from T1 to T4, from Tc to Td. Tc is greater than Td, so T1 is greater than T4. There is work done. W is greater than 0. The system performs work, which results in energy loss of the system, further resulting into a decrease in the temperature of the system from higher temperature T1 to lower temperature T4. Next, we have the isochoric process, which is characterized by constant volume. A constant volume process, so no work is done by the system. You'll recall that our equation for work done is integral of pressure dV. So if dV or delta V is 0, therefore work done is 0, which means that change in the internal energy of the system is just equal to Q. All energy added as heat remains in the system as an increase in internal energy. In the figure to the right, path 1,5 is an example of an isochoric process. From initial state 1 to final state 5, the volume is constant, which means work done is 0. In this process, the temperature changes from T1 to T5, from Tc to Te. Tc is greater than Te, so T1 is greater than T5. Heat flows into the system, resulting in an increase in the temperature of the system, resulting in an increase in the internal energy of the system. Next, we have the isobaric process. An isobaric process is a constant pressure process. So pressure is constant, which means our equation for work done by the system is now just equal to P times the change in the volume of the system, V2 minus V1. And the internal energy equation remains to be Q minus W. In the figure to the right, path 1, 2, is an example of an isobaric process. Initial state 1 to final state 2, the pressure is constant. The temperature increases from T1 to T2, from Tc to Ta. So T1 is less than T2, and there is work done. Work is equal to P times V2 minus V1. An isobaric process. And then there is the isothermal process. An isothermal process is a constant temperature process. Any heat flow must occur slowly enough that the thermal equilibrium is basically maintained, that the temperature is constant. For constant temperature, the ideal gas law equation tells us PV is equal to nRT if T is constant and the gas is constant. We do not change the gas. N is constant. R is constant. That means nRT is constant, which means PV, pressure times volume, is constant. So P1 V1 is equal to P2 V2 is equal to P3 V3 and so on. Pressure times volume is constant in an isothermal process. In general, none of the quantities, delta U, Q, or work is zero. They may be zero, but not necessarily zero. None of the quantities is zero. So the equation remains to be delta U is equal to Q minus W. Note, however, that if indeed we have an ideal gas, for an ideal gas, however, if the temperature is constant, the internal energy is found to be constant, which means delta U is zero. So for an isothermal process, in general, delta U may be any value. It's not necessarily zero. But if the system is comprised of an ideal gas, the delta U, the change in internal energy, is zero. Which means Q minus W is equal to zero. Q is equal to W. Any heat that flows into the system gets converted into work done by the system and vice versa. In the figure to the right, path 1,3 is an example of an isothermal process. So path 1,3, initial state 1 to initial state 3, the temperature remains to be constant at Tc. T1 is equal to T3 is equal to Tc. And work done is not equal to 0. Work done is greater than 0. So again, adiabatic process, delta U, no heat transfer, Q is equal to 0, therefore delta U is equal to negative W. Isochoric process, work done W is equal to 0, which means delta U is equal to Q. Isobaric process, pressure is constant, so we have an equation for the work done. Work is equal to P times V2 minus V1, and the equation remains to be delta U is equal to Q minus W. Isothermal process, temperature is constant, so we can use the ideal gas law equation. PV is equal to nRT. Since temperature T is constant, that means PV is equal to a constant value. In general, none of the quantities are 0. So delta U, Q, W in general, none of these quantities is equal to 0. Therefore, delta U is equal to Q minus W. But for an ideal gas, wherein we can apply the ideal gas law equation, for an ideal gas, if the temperature is constant, the change in internal energy is 0. Therefore, Q is equal to W. Speaking of ideal gas, let's take a closer look at the ideal gas law. For an ideal gas, the relationship between pressure, volume, and temperature is given by PV is equal to nRT, as we have mentioned in the previous slide. PV is equal to nRT. P is absolute pressure. V is the volume of the system or gas. And N is the number of moles of gas that is present in the sample or in the system. And capital R is known as the gas constant. It's equal to a constant value of 8.31 joules per mole Kelvin. So Kelvin, that means T, the temperature must be in Kelvin. So if it's given in some other temperature scale, say Celsius or Fahrenheit, you would have to convert the temperature to Kelvin before you use the ideal gas law. Provided that the gas density is low, the ideal gas law holds for any single gas or mixture. For a mixture of gases, the N, the number of moles, is equal to the total number of moles of the gases present in the mixture. So if the mixture is comprised of two gases, gas 1 and gas 2, and the density of the gases, the densities of the gases is low enough, we can apply the ideal gas law for the number of moles N. N will be equal to N of gas 1 plus N of gas 2, and so on. And that's it for now. In the next video, we will take a look at examples, the examples part of our discussion for the first law of thermodynamics. So thank you for watching.